Now we shall look at single sample t-test. Single sample t-test comes in two forms. One is called as with variance known, that is sigma square is known, and the other one is variance unknown. So you use a square instead of sigma square. So under these two conditions we use this t-test. Let's look at the first condition first, that is we know the population variance. If population variance is known, then we know that if we have one, so what all we know? We have some value of mu, okay, which comes from some hypothesis that I hypothesize that mu is a particular value, okay, so it's a population's mean. Then sigma square is a population variance, right? And x bar is a mean of a single sample, mean of single sample obtained, okay? And we also have n, which is the sample size. So we have obtained this x bar on a sample of a size n, right? Now we know what z is. Z is x minus mu upon sigma. Now our x is not x, we have x bar, right? So for us this would be z is equal to x bar minus the mean of the x bars is mu upon what is the standard deviation of x bar? We know that the standard deviation of x bar is sigma x bar, and we know that sigma x bar is equal to sigma upon square root of n, right? So I can rewrite this as x bar minus mu upon sigma upon square root of n, right? So this is my single sample z test. Now what is the requirement of the z test? I need to know sigma, okay? Mu is a hypothetical value. Mu is a hypothetical value. I want to test whether the sample mean that I have obtained come from the population that has mean mu, okay? But if I have to do z, I need to know the value of sigma. If the value of sigma is not known, then I can't use single sample t-test with variance known, and then I'll have to use an estimator of a variance. But right now we assume that we know this. Say for example, there is a test, say test of neuroticism, okay? We know that the population mean population mean for some large population, the mean of this neuroticism test is say 50. Okay. For some reason I believe that I also know the standard deviation of or the variance of neuroticism, this particular scale, and this variance is 49. So that I also know that the standard deviation is 7. I am taking 49 simply because then I get a simple standard deviation 7. Okay. Now, suppose I take a single sample. If I take a single sample and the sample's mean x bar is say 47. Okay, and the n for this problem suppose is 40, right? Now what I will do, I will compute z, which is here. X bar is one single sample mean that I have, that is 47. minus mu, that is 50, upon sigma. Sigma is 7 divided by square root of the sample size, that is 40. Right? So this is 3 divided by 7 upon square root of 50 is 3 upon okay, this is 1.067, right? Have you done that? 7 upon square root 50 is this value, which is equal to which is equal to 2.710. Right? This is the value that I have obtained. Now, this is Z. So this follows standard normal distribution. I know that I'm erasing this. I know that standard normal distribution has a mean 0 and variance of 1. Right? This may not look like standard normal distribution, but that's fine. Okay? There's a mean 0, variance of 1. Now, what I have obtained is 2.710. 2.710, this side, say this is 1, 2, 2.710, this is positive 2.710, this is negative 2.710. Okay? So, I want to know the area beyond this, positive and negative 2.710. So what I want to know is I wish to integrate the area beyond this, and I wish to integrate the area beyond this. Or what I would simply ask is, if I set my alpha, that is type 1 error, at 0.05, then I also know that probability that Z would be greater than plus minus 1.96 is equal to 0.05. Right? So probability that I would get a Z of 1.96, that's either smaller than 1.96 or greater than 1.96 is 0.05. Okay, so this probability, since I know, I also know, so which means that 1.96 is here, 1.96 is here. So any value that would lie beyond 1.96 of Z, okay, any value which lie beyond 1.96 Z has a probability of smaller than 0.05. Since the value we have obtained in this calculation is 2.710 is greater than 1.96, I say that probability of Z being equal to 2.710 is smaller than 0.05. Right? This probability that I will get a Z of this is smaller than 0.05 because it is away from is greater than 1.96, and so I say that my null hypothesis that mu is equal to 50, that is an alternate hypothesis that mu is not equal to 50. I cannot retain my this null hypothesis, and I perhaps reject the null and accept the alternative. So the sample mean that I have obtained 47 comes from a population that does not have a mean 50. It comes from some other population. What is the mean of that population? I cannot answer with this, but I can answer a question that this particular value that I have obtained, this particular sample, is less likely to come from a population that has a mean 50. Perhaps, see, I would perhaps say that it has come from a population that has mean 50 when it falls between these values. So had the z been smaller than 1.96, positive, negative, then I would have said, so if the z has fallen between negative 1.96 to positive 1.96, I would have said that the value that I have obtained, the sample mean that I have observed, comes from a population that has a mean 50. Since it has fallen outside, it is, I will say, it comes from a population that does not have a mean 50. This is single sample t-test with population variance, no.